So now let's move on to the second question. What happens if the block is already moving? So here we have the block moving up the hill, and we're asked what its acceleration is. Because the block is moving, static friction isn't important. Instead, we're going to be looking at the kinetic friction, UK. So we're going to make a note of that. We've got mu k, changed color for some reason, is equal to 0.1. Once we've got the information from the problem, we can go ahead and get rid of the text. Now, what we're going to do is going to follow pretty much the same procedure as part A. So we've got the same forces. We have gravity pointing down, and its size is still going to be mg. We have the normal force pointing outward. So these two parts haven't changed. We also have friction, but we need to think a little bit more carefully about which direction friction is going. The block is moving up the hill, so in this instance, friction is going to try and oppose that motion, and friction is going to point down the hill. Right. So this is the hard part, getting the direction of friction right, because the bottom of the block is moving up the hill and it's rubbing against this. Friction is going to try and bring these two surfaces to rest. Okay. Just like last time, we're going to break the gravitational force into components. And because the gravitational force is still pointing in exactly the same direction, the answer for these components is going to be the same as last time too. We're going to have an mg cosine 25 degrees and an mg sine 25 degrees. So I don't want you to think that this problem is easier, it's just we've done all the work from the previous problem, and so that's why we're able to go through this so much quicker. So let's move the force of gravity so that it's sort of more obviously pointing in the parallel direction. Okay. And again, we want to get rid of this blue arrow because getting rid of the force of gravity, we're getting rid of the force of gravity because we've already included it by having these two components. Okay, so now it's time to find the net force, and again we do it by looking at the perpendicular part and the parallel part completely separately. So here's our perpendicular part, and here's our parallel part. Okay, in the perpendicular direction, the only forces that we have are the normal force and this component of gravity. So F net in the perpendicular direction is equal to the normal force minus mg cosine 25 degrees. Okay. And for the same reasons as last time, we know there's no acceleration in this direction. The normal force gets as big as it needs to get to stop the block sinking into the surface, but it doesn't get so big that it's going to bounce off. So there's no acceleration in this direction. So again, reminding ourselves, this part comes from the force diagram, whereas this part, the zero, comes from knowing about the acceleration. It comes from F net equals ma. So exactly the same way as part A, we have the normal force is equal to mg cosine 25 degrees. Or the normal force is going to be equal to, putting in all the numbers, 18.13 newtons. The only real difference is, in this case, the net force in the parallel direction is going to be pointing down the hill. So we have mg sine 25 degrees like last time, but in this case we're adding on the force of friction. Friction and this component of gravity point in the same direction. So last time we worked out what mg sine 25 degrees was. We figured that that was 8.45 newtons just by putting in numbers. Okay, but how do we find the size of the frictional force? Well, for kinetic friction, it's pretty easy. Once we know the normal force, we can find the frictional force by multiplying by the coefficient of kinetic friction. So since the normal force is 18.13, we know the friction force is 0.1 times 18.13, or we know that it's 1.81 newtons. So the net force in the parallel direction is 8.45 newtons plus the 1.81 newtons we have from friction, giving us a grand total of 10.26 newtons. Okay, and it's in the positive direction. That is that the net force points down here. Okay, notice that I'm not putting the net force on the force diagram because it's not a force being applied to the block. It's what I get when I add all of these forces together. So the question was to find the acceleration of the block. Well, the acceleration in the parallel direction is F net in the parallel direction divided by the mass. So it's 10.26 newtons divided by the mass of the block, 2 kilograms, which gives me an acceleration of 5.13 meters per second. And this acceleration is down the hill. So even though the block is moving up the hill, the acceleration is pointing down. This makes sense because the block is slowing down. So here's our summary for how we draw these force diagrams. We start off by identifying the unknown. In both of these examples, it was the acceleration. Then we look for the possible forces just by thinking about what objects are in contact with the block in this case and what long-range forces should be applied. And then we write down the forces on the diagram and we use those forces to find the net force. The very last step is we have to make sure that our answer is consistent with the second law. That is, that the net force we get by putting in F equals ma gives me the same answer as the net force that I get by adding all the forces on the diagram. Another important point from this is that forces like the net force or static friction don't actually have formula to figure out how big they are. Instead, we use information about the block, such as it's not going into the surface or bouncing out, to tell us something about the acceleration in a particular direction. These forces are typically the last ones we're ever able to work out, because we have to work everything else out first. Forces like gravity or kinetic friction are different. There we can stick in formulas. The force of gravity is mg. The force of kinetic friction is just mu times the normal force. So we can figure those forces out unambiguously, and they're probably the better places to start.